All right, so let's get started. All right, so question 1, which of the following shows the correct classification and expected monoatomic ion charge for the given element? We have a periodic table in this room over to your right, so we can look over at that when we need to, so I don't have to keep pulling it up. Here, actually, I'll probably pull it up on here just so people that are watching the video can tell what the heck I'm doing. So you'll see it up here or to your right. All right, so we have 3 possibilities here: potassium, aluminum, selenium, and we want to know if the classification and the charge is correct. All right, so for potassium, we find it in the periodic table. We need to know the atomic symbol for potassium, which is K. Sorry. Okay, I guess we can see that. All right, so potassium is in group 1 of the periodic table. I'll point to it here so that people watching at home can see. It's element number 19, so that means it's a main group metal. So the metals are on the left side of the periodic table, and those that are in the S block here, the first 2 columns, or in the P block, there's a few metals. Those are all considered main group metals. So the first 2 parts of this are okay, but if we think about the charge, this should be +1. So potassium should be a +1 charge, so that charge that's given is not correct. Number 2 is aluminum. All right, so aluminum is atomic symbol Al. We find it's number 13 on the periodic table, over there if you're looking at that periodic table. All right, so aluminum is atomic number 13, and it's also a main group metal. So that staircase is going to go down like this, and aluminum is to the left of the staircase. So the staircase goes like that. So aluminum is to the left. It's one of those rare P block metals. So aluminum is a main group metal, and the charge is going to be +3. All right, now if we want to rationalize why does aluminum form a +3 charge, the configuration is 3s2, 3p1. So it loses all 3 of those valence electrons to form a stable +3 cation. So this one's good. And then finally we have selenium, nonmetal, -2. Back to our periodic table. Selenium is atomic number 34. It's in group 6A, so that means it's going to gain 2 more electrons to form a noble gas configuration, and 2- is the correct charge, so this one's good too. It's also a nonmetal because it's to the right of the periodic table. So that means the correct answer for this is choice E. So there will be questions on the test about classifying elements, nonmetals, metals, transition metals, all that good stuff, and being able to predict the charges of ions is important as well, both by itself and also for the nomenclature of ionic compounds. Let me change this a little bit. Okay. All right, so any questions on that one? All right, pretty straightforward. Let's move to number 2 then. How many neutrons and electrons are present in a 55 manganese 3+ ion? All right, so Mn is manganese, and to do this we have to know the anatomy of the symbol. So 55 Mn3+. So remember that the number on the top left tells us the sum of the protons and neutrons in the nucleus. Now, we're not asked directly about the number of protons for this problem, but it's still helpful to know because we're going to need that both to determine the number of electrons and the number of neutrons, which we're asked about. So if we want to know the number of protons, that comes from the periodic table and the atomic number. So we just find Mn on the periodic table. It's a transition metal, and it's atomic number 25. So it's right here in the middle of the first transition metal series. All right, so the number of protons we can get very easily from the periodic table. That's 25. So that one we don't even really have to think about. And that means the number of neutrons, which is part of this answer, is going to be this number here, 55, minus the number of protons. That number 55 is the sum of the 2. All right, so we have 30 neutrons. That's part of our answer. So we can eliminate C, D, and E right away if we're confident in that. But then we need to know the number of electrons present. So the number of electrons is going to be the number of protons, then we have to account for the charge. So if it's a neutral atom, the sum of the protons and electrons have to be equal. But here we have a net +3 charge. That's what the symbol tells us. So we need to subtract 3 electrons for that. Okay, remember, if it's a positive charge, you have excess protons or a deficiency of electrons, so you need to subtract 3. So this is for that +3 charge. We have 3 less electrons than protons. And so 25 minus 3 is 22. And so that means the only choice that has both of those correct is choice B. All right. So number of protons is usually the easy one, because if you can find the symbol on the periodic table, the atomic number, which is the number that's above that symbol, is going to tell you how many protons there are right away. All right, questions on that topic at all? Okay, moving on. All right, this is something we just talked about today, so if you're a little bit hesitant on this one, you have time still. I just covered it, 20 minutes ago or whatever. So give the chemical formula for tetraphosphorus DEC oxide. And then we're, entering these in on Blackboard, you would be, entering in without subscripts, just the numbers and the letters. So we go to the name, and we look at the elements that are involved. So we have phosphorus and oxide, so phosphorus and oxygen. We should recognize that those are both nonmetals because they're both in the top right of the periodic table. Phosphorus is number 15, oxygen number 8. So they're 2 nonmetals forming a compound, so they're a covalent compound, which means they follow those rules for covalent compounds which involve prefixes. So the prefixes are there, right, staring us in the face anyway, but because of that, we know that these first parts of the names are going to tell us how many of each there are. Tetra and dec. So tetra is 4. Deca, which if you could have an A in it, also is 10. So dec or deca is 10. And so that means we have 4 phosphoruses and then 10 oxygens. Now, if you're entering this into Blackboard, of course, we don't do subscripts in Blackboard. Just write P4 O10. Okay, but that's the answer. So when you do there'll be questions on the homework and the practice test that involve you entering in answers. Just make sure you practice getting the right format. It's typically straightforward, but don't do any, follow the instructions very carefully and don't do anything too rogue on those, because it does interpret your answer very literally. So no spaces, just the numbers and the letters for these types of questions. All right, anything about nomenclature you want me to review, since I just went over it today, but anything that I didn't go over well enough? Nope. All right.
This wouldn't be reduced because it's a covalent compound.
Exactly. Yep. So for covalent compounds, we leave the numbers as is. The prefixes tell us exactly how many there are, and we don't change those numbers to any smaller ratio. Because, P2O5 is another compound. It's a different compound, actually. So it does exist, but it's not the same thing. All right. Good question, though. And now finally, we're going to do names of ionic compounds. All right, so these, we have to know the rules for ionic compounds. And we also have to know the charges of everything involved. So if we have strontium 2 carbonate, that tells us that we have Sr2 plus. And then carbonate is one of those polyatomic ions that we need to learn, which is CO3 2 minus. So if we combine a 2 plus cation with a 2 minus ion, SrCO3, that's the correct formula. Now, there's a problem with this name, though. Does anybody see it? Sorry? Oh. Say that again? It does not need to have parentheses, correct. No. So carbonic would be for the acid. So if you're just naming an ionic compound, you just keep the ATE ending. The problem with this name, though, is that we have this Roman numeral 2. And remember, we don't use Roman numerals for main group metals. All right, so strontium is in the second column of the periodic table. Let me finish writing what I was going to say. So no Roman numerals. All right, so just by looking at the first answer choice, that's the correct answer. I'll go through the rest of them to convince ourselves that those are the correct name and formula. So we're picking the one here that is incorrect. So strontium is a main group metal. So if we go to the periodic table, strontium is down here, Sr number 38. We saw it in class today, another example. So this is in the second column of the periodic table, which means that it's always going to be a +2 charge. So for those main group metals, these two columns here specifically, group 1A, group 2A, we don't have to indicate the charge in parentheses in the name. It would just be strontium carbonate. Okay, so we don't have this. That's not supposed to be there. So that's why that one's incorrect. Now let's go through the rest of them and convince ourselves it's right. So cobalt-2 nitride. All right, so cobalt-2 in parentheses tells us that it's cobalt-2 plus. Cobalt is definitely a transition metal. It's right here in the middle, number 27, not too far from manganese that we saw earlier. So because it's in the D block of the periodic table, cobalt right there, because of that we need to put the charge in parentheses, and that's going to tell us it's 2 plus. And then we have nitride. So the charge on nitride, nitrogen is in group 5A. And we go over 3 more to get to the noble gas configuration. So nitrogen, when it's in ionic compounds, makes a 3- charge. That's invariant. All the nonmetals have a defined charge, which gets them to the noble gas configuration. And the formula here is CO3N2. So we have 3 2+ cations and 2 3- anions. The charge balances out. Everything works out. So this one's good. If we do calcium phosphate, the next one, Ca3PO4 So nothing wrong with the name because calcium is also a main group metal, so we don't need to put any parentheses or any Roman numerals there. Phosphate is the correct name for this anion, PO4 3-. Now if we think about the charge of these, though, we have to know the charge to evaluate if the formula is correct. Ca3 2+, so we have 3 calcium 2 pluses. Calcium is always 2 plus. And then for phosphate, it's PO4 3-. Okay, so this is one of our 3- anions, or I think the only one that we'll have, and there's 2 of those. So just like we saw before, we have a +6 charge from the cations, a -6 charge from the anions. 3 2 pluses, 2 3 minuses. The charges balance out, so the formula is also correct. So what I'm doing now is verifying that the formula is correct. Okay, zinc sulfide. So I didn't talk about this in class today, but zinc is the weird transition metal. It's the only one where we don't have to put Roman numerals on it because zinc is always 2 plus. I don't think this will come up on your test anyway, but zinc is right here in the periodic table, number 30, and it always forms 2+ cations for reasons we might get into later on in the course. But anyway, if we know that zinc is 2 plus, okay, sulfur is in group 6A of the periodic table. It's atomic number 16, so sulfur will also form 2- anions. So if you have a 2+ cation and a 2- anion, the correct formula is Z and S, one of each. So that works out. And then finally, potassium chlorite. Potassium is in group 1A, over here, number 19. So it forms a 1+ cation. And then chlorite is ClO2 with a 1- charge. So there's 3 of these chlorine oxygen anions that 4 of them that we have to learn. So this is the correct name and formula, and then this is in your book if you're gonna study that table. But there's a lot of these similar ones. These are probably the hardest ones to learn. So we have ClO- is hypochlorite. And then we have ClO2- is chlorite. ClO3- is chlorate. And then ClO4- is perchlorate. All right, so there are a few examples of polyatomic anions where you have the same elements in different ratios forming those anions. And for most cases, you would have either 2 or 3 oxygens or 3 or 4 oxygens. You only have 2 options. That's where the ite endings come in. So if you have less oxygens, you get an ITE ending. If you have more oxygens, you get the ATE ending. Hypo means fewest, per means the most. So learn, these 4 are the hardest ones to learn, but learn those 4. And then also, all of the other halogens have anions based on this. So if you have IO-, that would be hypoiodite, and so on. So you can replace this chlor with any of the, pretty much any of the elements in here, specifically bromine and iodine as well. Yep. So that's one of the polyatomic anions that you're just going to have to learn.
Okay, same with chloride, like all of them.
Yeah, so any of these groupings of atoms that are, PO4 3-, ClO2-, those have a fixed charge. Now, the nice thing is if you have 2 different anions with the same element, and then they tend to have the same charge. So there's phosphite and phosphate. They're both 3-. All these chlorate ones are 1 minus, nitrite, all 1 minus. So the charges are a little bit easier to remember, but you have to remember, how many of each element there are, and they get slightly different names because of that. All right, anything else on ionic nomenclature? Yep.
You have the 2 plus and the 3 minus. I mean, where you cross them, is that how?
Yes, yeah. So there's 2 ways to think about it. Yeah, right. If you cross the charges, you would get this 2 plus goes down here as a 2, and this 3 minus goes down here as a 3. So CO2O3 or N3. Sorry, CO3N2. And then if you look at the charges of these, they should balance out. So there's 3 2 plus cations, which is plus 6, and there's 2 3 minus anions, which is minus 6. Plus 6 and minus 6 completely cancel out. So that's you can think about it either way, but that's where that crossing rule comes from is by the need to balance the charges of the cations and the anions. But yes, you're correct on that. Yep. At this point, you're probably going to have to memorize it. I mean, if you, once you get really good at drawing Lewis structures, you can draw the structures and figure out what the best charge is going to be to make a stable species, but we're not quite there yet. So I think at this point, the best thing is just to memorize the charges of the anions. There's not an easy way to rationalize them at this point. All right, anything else? All right, so let's move on to number 5. So now we're back into older stuff, back to chapter 1 or 2, I forget which one. An infrared photon has a wavelength of 1234 nanometers. What are the energy and frequency of the photon? So for photons, which are little packets of light energy, there's basically 3 equations we need to know, and 2 of them are derived from each other. So the first one is the energy equation. So the energy of a photon is equal to h times nu, which is the frequency, and then we also have lambda times nu equals c. So these are the 2 basic equations, and then from these equations we can derive a third one, which is to replace nu with c over lambda in this equation. All right. So if you know these first 2 equations that I wrote, you'll know everything you need to know, but we can derive another one that's very useful sometimes as well, so we don't have to always do 2 steps for everything. We can make that substitution beforehand. So we have these 3 equations that deal with the energy, wavelength, and frequency of light, and we want to make sure we know how to use them and interconvert between those values. So when we do this first one, we have a wavelength of 1234, and we want to know the energy, so we're going to plug that into the energy equation, which is hc over lambda. So h and c are constants. They're on the periodic table, so I'll show you those. This little recording thing is going to block you guys. But anyway, the h is Planck's constant, which is here 6.626 times 10 to the minus 34. And then the speed of light c, which is down there, is 3 times 10 to the 8th. So those are both on your periodic table, so don't need to memorize those. But we're going to use them a lot on this test. So we have those 2 constants, which we don't want to change their values. Now when we're doing this, we need to put the wavelength in the correct units. So lambda needs to always be entered in as meters when we're using this equation. Because we have meters per second for our speed of light, we want meters to cancel out. So our wavelength is very often going to be given to us in nanometers or occasionally in other units. We need to convert it to meters and know how to do that. So the wavelength in meters is going to be 1234 nanometers. And then this conversion that we're going to have to use a lot is 1 meter is 10 to the 9th nanometers. Or 10 to the minus 9 meters is 1 nanometer, however you want to write it. But it's the same thing either way. And that gives us 1.234 times 10 to the minus 6 meters. All right, so that's going to be the number we want to put in for lambda into that first equation. All right, so if we punch in the numbers to our calculator, we should get 1.61 times 10 to the minus 19 joules. All right, so we should be starting to be familiar with this. Photon energies are usually on the order of 10 to the minus 18, 10 to the minus 19. So if you get something way different than that, definitely check your work. All right? And then finally, if we have the second part, which is the frequency, now that we have the energy and the wavelength, we can use either of these equations to find frequency. It'll give us the same number. Let's use the wavelength equation since that's what we're given. So if we solve for frequency, nu is equal to c over lambda. So we have 3 times 10 to the 8th meters per second, leaving out some sig figs. And then we're going to use the same value of lambda. It has to be in meters once again to cancel out the units in the numerator. So 1.234 times 10 to the minus 6 meters. You get 2.43 times 10 to the 14 hertz. All right, so those are the two values. So the only answer choice that has both of those correct is choice A. Okay, any questions on using those equations just by themselves? Yep.
Are we going to have the equations in this?
Not these ones, no. I don't think we're... Sometimes in the problems we give you equations, but typically not these ones. Yep.
Are we going to have to worry about sig figs?
Sig figs I don't think are going to be a big concern because the questions are usually multiple choice, and if they're not, we're going to specify how many decimal places to enter in so we don't have any rounding errors causing huge problems. So what I would recommend when you're doing problems in Blackboard, I mean, I'll always check your answers, and if you were like really close and it got marked wrong, I'll often give you the benefit of the doubt. But to be safe, do all the rounding at the end, and make sure you follow our instructions for how many decimal places to put in if we specify, okay? So when you're doing these tests in Blackboard, we're usually going to be very clear about how many decimal points to add in, and try not to do any rounding until the very end to save yourself from any errors like that. Yep. So the lambda has to be in meters because we want, we're using our constants here, 3 times 10 to the 8th meters per second. So the units will also divide. So if we look at units for this first one here, meters divides out, this second cancels out with that seconds, and that gives us an answer in joules. So if we don't have lambda in meters, then all the units aren't going to work out, and we're going to get an answer that's not right. Okay, so you need to pay attention to units, as I've been saying over and over again, but for these types of problems, just to be safe, always put it in meters and it'll work out. Okay? All right, moving on. All right, so this is just a conceptual problem. Either you know it or you don't. Which of the following are correctly ordered in order of increasing energy? So remember that electromagnetic radiation, it's waves of energy, which we now know has particle-like property that we call photons. But the properties of those are the wavelength and the frequency, which are interrelated to each other, and that's going to determine the energy of the radiation and then the type of behavior it has. And so over the years we've sort of arbitrarily classified them into different categories based on their relative energy and wavelength. All right, so the scale that we have, if we have frequency and energy increasing left to right, remember that wavelength is inversely related to those, so that would mean wavelength increases right to left. So there's 7 categories of light you have to know. And the easy way to remember this, I think, is to put visible light in the middle. That's the light that we see. So Roy G. Biv, everybody's favorite, what do they call those? Mnemonic device. There you go. So Roy G. Biv, that's your visible light. And then we have 3 that are below that in energy and 3 that are above that in energy. So immediately below visible is infrared. It's below red. That's why it gets that name. Below that is microwave. And then finally the lowest is radio waves. So when you listen to the radio, which I realize very few people do anymore, you're listening to, you're transmitting the signal with very low energy radiation, which is why it's safe to have it floating around your heads all the time. And then finally, if we go above visible, the one that's directly above it is ultraviolet UV, so that means above violet, above the blue or violet region of the spectrum. We have then X-ray, and the highest energy are called gamma rays. All right, so those are the 7 you have to know, and you have to know what order they come in. And so here in this problem, we're looking at increasing energy. So that's going to be, on this scale here, left to right. So it's going to be, we want radio to be lowest, then infrared, then ultraviolet, then gamma. So that should be choice D, I believe. Yep. All right, so know those 7 in order. Those are the different categories of light. All right, and then another type of problem we'll have from this section about energy quantization is calculating, wavelengths, frequencies, energies associated with moving an electron between energy levels in a hydrogen atom or a related type of atom. So when we see a question like this, the frequency of a photon needed to promote an electron from hydrogen's ground state into the third shell, we immediately should think of the Bohr equation. So very often with these types of questions, you're going to use the Bohr equation, which is in terms of energy. So this is an equation. Again, you should know this one. I don't think we'll always give it to you. But if you use it enough, it becomes second nature, like anything. So it's times z squared, and then we have 1 over nf squared minus 1 over ni squared, where these are the two different values of n that the electron is moving between. So when we have problems like this, we're going to zone in on this equation, and then very often what we're going to have to do, which is the case here, is we'll use this equation in combination with one of those photon energy equations that I told you about two questions ago. So you're going to use this equation first to find the difference in energy between the levels, and then you're going to use the energy of a photon, that equation, to figure out the wavelength or frequency associated with that transition. So it's a lot of times a two-part process. So if we're doing it for this one, we're promoting an electron, so we know that delta E should be positive. That means we're going from a low energy to a high energy, ground state into the third shell. So we're going lower to higher, which means positive delta E. And when we put the numbers into the equation, Z for hydrogen is 1, so a lot of these are going to be just for the hydrogen atom itself, but if you're talking about an ion that has more than one proton, like He plus or lithium 2 plus, you have to adjust the value of Z accordingly, which is the number of protons in the nucleus, but hydrogen just has 1. And then the values of N. So we're telling you that we're promoting it into the third shell, so that's your final value of N, 3. But there's a few cases where we're not going to actually give you a number for the first one. You have to figure it out from the wording of the problem. So remember that this term here, ground state, this tells us that N equals 1. So if we tell you it's going to or from the ground state, that means that value of N corresponds to 1. That's the lowest energy orbit, or the lowest energy position for an electron in a hydrogen atom. So that means our initial value of N is 1. So when we put these numbers in using the Bohr equation, we get an energy difference of 1.94 times 10 to the minus 18 joules. But the question is asking, what is the frequency of the photon needed to induce this transition? Because remember, when we're moving between energy levels in a hydrogen atom or any other atom, we're either absorbing light to take it to a higher energy, or if it moves to a lower energy, we're giving off that light. And the frequency and wavelength of that light are related to this energy value using those equations we already saw. So the energy of the photon that would promote this is equal to the absolute value of delta E. We can't have negative photon energies or negative photon wavelengths or frequencies. So we take the absolute value of that, and that's going to be equal to h times the frequency, or hc over lambda if we're solving for wavelength. All right, so that energy difference equals the energy of the photon, and so the frequency is just going to be given by the absolute value of delta E over h, which for this question we have the value of delta E is 1.94 times 10 to the minus 18 joules, and then h is that fundamental constant, 6.626. joules per second. So joules cancel out. That'll give us an answer in inverse seconds, which is hertz, and that comes out to 2.924 times 10 to the 15 hertz. Now, as is very often the case on the real exam, when you have an answer like this that's, an exponent 10 to the whatever power, we're usually going to have you take the log of that and report it, because Blackboard is, well, it's terrible at a lot of things, but it's especially terrible at handling exponents. So we'll ask you to take the log. So again, know where the log key is on your calculator, know how to use it. Because when you're entering this answer into Blackboard, there's no good way to do it for these exponents, so you're going to take the logarithm and report that. So the log of this frequency, if you're keeping score at home, is 15.47. So usually we'll have you enter the log to 2 decimal places. So a lot of times for problems like this, you'll enter an answer like that. So you solve the problem first, and then you take the log. It's one additional, but hopefully fairly trivial step to do that. Yep.
What would be an example of
So if you have a Z that you'd have to alter would be, this equation applies to any ion that only has one electron. So there's the only other ones that we would really have would be like helium plus, where Z equals 2. The atomic number on the periodic table is 2. Lithium 2 plus, Z equals 3. Beryllium 3 plus, Z equals 4. You could hypothetically do it for anything, but it has to be one electron, so it's, in reality, there's not many things in real life that satisfy that criterion. Is there another question? Nope? Yep.
Will the ground state always be 1?
Yeah, the ground state is always n equals 1. Now, there's one other case where you wouldn't be given the exact value of n, but you'd have to deduce it from the problem, at least that I can think of. So if you have an excited state, that tells you that's a higher energy levy, so that means n is greater than 1. So if we say first excited state, that means n equals 2. That's the first state above the ground state. Excited state means above the ground state. The second would be n equals 3, and so on. So we might use the terminology excited state as well. You'll have to interpret the value of n from that. So ground state means n equals 1. Excited state means n is higher than 1. Yep.
Is there a reason that you're using this one instead of the Rydberg equation?
I'm not using the Rydberg equation because I didn't teach it to you.
I only asked because Rydberg's written on the periodic table.
That it is, yeah. So your book doesn't cover Rydberg. I covered it last year. I mean, so the point about, if you know what the Rydberg equation is, it's basically this equation rewritten in terms of wavelength, or actually inverse wavelength. And it can be useful, and really the point is that either this equation or the Rydberg equation can be used in any situation. You might have to then do something different with your answer once you have it, but if you know this equation or if you know the Rydberg equation, any of those will be useful for any of these types of problems. You just have to know what the quantity means that you solve for, and then be able to use these types of equations to get the answer that you want at the end. So if you're more comfortable with the Rydberg equation, if you learned that in a previous course, or you have a different version of the textbook that has that, you're welcome to use it, but I didn't cover it in this course because it's not covered in your textbook. But that's certainly valid. Yep. How did I do the log? So that's just with a calculator. So the log is just the log base. It's always going to be natural, sorry, not natural log base 10. We'll specify that, but log base 10. So 2.924 times 10 to the 15th, and then, at least in my calculator, I just press the log key, and that gives me 15.47. So some calculators are different, so make sure you're familiar with whatever one you're going to be using on the exam. Yeah?
So if you get that answer, you have to do the units or?
No, so another good point is that when you're entering, guys, it's hard to talk over everyone, sorry. When you're entering numbers into Blackboard, don't put units on it. We're going to specify that, but units would cause too many problems with typos or abbreviations being slightly off, so don't put any units in your answers unless we ask for it, which I don't think we ever will. But the directions will be very clear, but when in doubt, leave the units out. Okay, good point. And a log never has units anyway, so in this case it's a moot point. But even for a numerical answer that should have units, leave them out when you enter it into Blackboard. So we'll tell you what units that you should have the answer in, but you don't actually put those into the answer when you type it into Blackboard, if that makes sense. Okay, I think we should move on to number 8. Which of the following is a valid set of quantum numbers for a 4D orbital? So the first thing we have to do is we're given 4D, so let's figure out which quantum numbers that tells us. So remember that when we have a subshell, which is a number followed by a letter, that tells us the first quantum number, which is n, that's just the number. And then this tells us the value of L, but of course it's not in numerical form, it's in letter form. So if we have L is equal to 0, 1, 2, 3, these are the ones that we'll see most frequently in real atoms. That means that the designations for this are S, P, D, and F. Okay, so that means in a 4D subshell, L equals 2. All right, so know those letters and know how they correspond, especially S, P, D, F, which are the 4 that occur in real atoms. Okay, so we have n equals 4, L equals 2. So if we look at these sets of quantum numbers, okay, all of them have the correct value of n. The first quantum number is 4. Well, if you look at the value of the second quantum number, this one is L equals 1, this one's L equals 3. So both of these, C and E, have the wrong L value. All right, so if we're trying to find the valid set of quantum numbers, we now need to look at this third quantum number in this group, which is M sub L. So to do this, we have L equals 2, and we have to think about the valid allowed values for M sub L. So M sub L can be any value that ranges from minus L, including 0, up to plus L. Okay, so when you have a value of L given to you, in this case it's 2, that means our M sub L can be minus 2, minus 1, 0, plus 1, and plus 2. So it has to be an integer value, so choice D is out because this is not even a allowed value of M sub L. They're never non-integers, always 0, 1, 2, 3, or minus negative numbers. And then if we go to choice B here, this 3 here is wrong. That's an invalid value for M sub L. So M sub L cannot be bigger than 2 if L equals 2. So plus 2 is the highest allowed value. This one has 3, so choice A is the only one where everything checks out. So minus 2 is an okay value for M sub L with these. So know the relationships between quantum numbers because that'll tell you the allowed values and how many of each type there are. Okay, questions on this topic? Good. Let's move on. And then another type of question you'll see related to orbitals and subshells is how many orbitals are in the sublevel where n equals 5, L equals 4, something along those lines. How many orbitals, how many electrons for a given shell or a given subshell, whatever the case may be. So for these ones, we just need to look at the given information, and there's 2 simple equations that allow us to determine whether, determine the answer to this type of question. Now, another way to do this is to write out all possible values of the quantum numbers, but that can take a while, especially for this one where we have a pretty large value of n and L. We would be writing quantum numbers for a long time, and it'd be easy to miss one. So I suggest that you familiarize yourself with these very simple equations that I'll show you and allow you to do that. So if you're given n and L, or just L, because this equation only depends on L, the number of orbitals that would have that in that subshell is 2L plus 1. So that's the number of orbitals, and then the number of electrons would be twice that because there's 2 electrons per orbital. So if you know the value of L for a subshell, this is how many orbitals are in that subshell. And so for L equals 4, 2 times 4 plus 1 is equal to 9. Now this didn't come into play in this problem, but if you're only given n, the first quantum number, if you're given n only, the number of orbitals is just equal to n squared. All right, so those 2 relationships and then doubling those relationships to get the number of electrons could be important. All right, so if you know the value of L, use 2L plus 1 for the number of orbitals. If you only know the value of n, use n squared. Okay? Questions on that? Yeah. Yeah, the number of electrons would be 2n squared for a given value of n for a given shell. And then for a subshell, it would be 2 times 2L plus 1. And that also comes from the periodic table, which, especially for subshells, it's easy to read because on the periodic table, the S part of the periodic table, which are these first 2 columns here. Oh, you guys can't see my hand, can you? Oh, there it is, yeah. So those are two elements, which means there's 2 electrons in an S subshell. 2 times 2L plus 1 is 2. For the P subshell, 2L plus 1 is 3, and then 2 times 2L plus 1 is 6. So there's 6 elements in the P subshell. And then for the D, it's 10, and so on. So for subshells, especially for the ones that occur in real atoms, you can just look at the periodic table to figure out how many electrons are allowed in that subshell just based on how many elements wide is that block of the periodic table. In this case, there is no L equals 4 subshell on the periodic table. That doesn't exist in real atoms. You had to use the equation, the relationship, to get it this time. Yep? Well, that's why we have to look at the given information. So we're given n and L here, so you have to use this equation. So if you were to use 25, that would tell you that there's 25 orbitals in the n equals 5 shell. But from this equation, we know that only 9 of those occur in the L equals 4 subshell. So out of those 25 orbitals, there'd be 9 that are in 4. There'd be 7 in 3, 5 in 2, 3 with L equals 1, and 1 with L equals 0. So they're divided up into different subshells based on this equation, 2L plus 1. Okay. All right. I think we should move on if there's no other questions. If you have to leave early, of course, go ahead. These people are setting the, taking the lead and doing that, so don't feel bad about it. I realize that I might have something else going on today besides chemistry. All right, so number 10, and then we'll be halfway home. So how many radial nodes and nodal planes are found in the probability contour for a 4D orbital? All right, so the probability contour is just a fancy way of saying shape, and we want to know how many nodes of each type are in this. So again, for this one, there's some simple relationships that we can be aware of that will help us answer these types of questions. So we talked about radial probability distributions, and then we ended up drawing the shapes of orbitals. So the value of L tells you the basic shape of the orbital. So both of these answers are going to depend on the value of L in some way. So we're talking about 4D again, which is n equals 4, L equals 2. So the easy one is the number of nodal planes. That's just equal to the value of L. Okay, so remember the value of L tells you the shape of the orbital, and that shape is determined by the number of nodal planes in the orbital, whether it's a simple sphere or a dumbbell shape or a four-leaf clover, those possibilities that we saw in class. L equals 2. So for example, a d orbital, remember most of them have this basic shape. And a nodal plane would be a plane that cuts the orbital in half, and the sign changes as you go across that plane. So there'd be a plane like this that cuts it in half, and another one like this. So a d orbital has 2 nodal planes that cut it along either direction like that. It'd be a plane that's sort of perpendicular to the board as I've drawn it. Okay. So that's what a nodal plane is. We don't really have to know that definition too well, but if you want to know how many of them are, you just use this simple relationship. The number of radial nodes is a little bit different. A little bit more complicated, but not too bad. So that's n minus L minus 1. All right, so if you know the value of n and L, you can predict the number of radial nodes that are present. Those are values, those are distances from the nucleus where the electron can exist. And so for this one, n is 4, L equals 2, 4 minus 2 minus 1 is 1. So this should have 2 nodal planes and 1 radial node, which is choice B. Let me check real quick to make sure my video is still going. We're good. All right, so then Well, you should know the shapes of the s, p, and d orbitals. So this is d. P have this shape, whoops. And then s is just a sphere. So you should know those 3 and something about their orientations. Remember, for the d orbital, the name of the d orbital tells you how it's oriented on the axis, and same with the p orbital. So you should be able to recognize the shapes. Obviously, you don't have to draw them because we can't draw on Blackboard. Be familiar with those shapes, and it'll also be important moving on to the next section of the course as well. So it's something you definitely want to learn, if not for this test, for the future. Okay, and then the other thing I want to point out, when you're talking about radial nodes, another way to think about it is it's the number of orbitals of that type that occur at a lower value of n. Okay, so what I mean by that. So 4D is the second shell that has d orbitals. Remember, 3D is the first d orbital subshell, and then you have 4D. So there's one shell below 4 that has d orbitals, so there's 1 radial node. That's another way that you can think about that relationship. But this equation, n minus L minus 1, is really where that comes from. All right, any other questions on this? All right. As Bon Jovi once said, we're halfway there. So here we go, number 11. 2-part answer. What is the maximum number of electrons allowed in the n equals 5 shell, and how many of these can reside in the 5f subshell? So this gets back to a problem I just talked about a little bit ago. I already gave you these relationships. So for a given value of n, the number of electrons is equal to 2n squared. Remember, n squared is the number of orbitals. You double that to get the number of electrons. So for this problem, it's 2 times 5 squared equals 50. So that means in the n equals 5 shell, you can fit a maximum of 50 electrons. But the second part of this question is, how many of those can be in the 5f subshell? So remember, the fifth shell is going to have 5 different subshells. It's going to have S, P, D, F, and then one other one, G, which electrons can go in all of those. We want to know how many of those go into 5f. And here we have a value of L. And again, the number of electrons is 2 times 2L plus 1. So we have to figure out the value of L. We're in an F subshell, so that corresponds to L equals 3, as we saw before. Okay, so we have an L equals 3 subshell. 2 times 3 is 6, plus 1 is 7, so then we double that. So 14 of those 50 electrons go into the 5F subshell. The rest would go into other subshells. All right, so that means the only answer that works is choice C. All right, so that's the same relationship we saw before, just time for the number of electrons instead of the number of orbitals. Okay, good. All right, and then number 12. Which of the following orbital diagrams represents an atom in the ground state? So when we're thinking about ground state configurations, and if we're given diagrams like this that show both the arrangement of the electrons and the spins that are either up or down, we have to think about 3 basic rules and make sure that all of them are followed. So the first is the off-bow principle. This means we fill from lowest to highest subshell energies. Now the implication of this rule for these types of diagrams is that all of the lower energy subshells should be completely filled before you start adding electrons to the highest subshell. So in other words, you should only have one partially filled subshell in your diagram. There's 2 exceptions to that, chromium and copper, where you promote electrons. But in general, you're only going to have one partially filled subshell. If you have more than one, you're violating the off-bow principle. So that's the problem here with choice B, okay, because this guy violates off-bow. Because as we see in choice B, you have 2 electrons and 1 s. That's good. But the 2s only has 1 electron. It can hold 2 electrons. So we would want to fill that before we started populating 2p. So in choice B, we violated the off-bow principle by skipping one of the spots in the 2s subshell before moving on to 2p. So that one's no good. And then if we have the second one we want to think about is Hund's rule. Which is to maximize unpaired electrons. Okay? So if we look at choice A, this one violates Hund's rules because Hund's rule, we only have one of them in this course. Because we have a partially filled subshell, we should have 2 electrons in 2 different orbitals, but they should have the same spin for Hund's rule to be followed. So in this case, one is spin up, one is spin down. That's a violation of Hund's rule. And then same with choice D. This one also violates Hund's rule. Because when we get to the 2p subshell, we should fill each orbital individually before we pair them up like this. So that's another violation of Hund's rule. And the only one that works is choice C. Now there's some confusion because you're like, well, wait a minute, you skipped a spot here. But remember, that's just by convention that we put them in order. But in reality, all that has to be true is that each orbital has only 1 electron and they have the same spin before you double them up. So it doesn't matter if we pick the first and the second, the first and the third, the second and the third. It just has to be 2 filled orbitals with the same spin to follow Hund's rule. Now the third one that we should be familiar with is, it didn't come into effect here, but for Pauli exclusion, that means no 2 electrons have the same quantum numbers. And it also means 2 electrons per orbital maximum. And if they're both in the same orbital, they have to be spin up and spin down. So none of these violated Pauli exclusion principle, but for example, if we had 2 spin up electrons in one of these orbitals, that would violate Pauli exclusion. If they're both in the same orbital, they have to be spin up and spin down. And you can have more than 2 of them in the same orbital as well. All right, so that's another one that might come into play. But for this one, we just evaluate off-bow principle and Hund's rule, and that zones in on choice C.
So it's not A because you have to fill all the orbitals with the same
Yes, so choice A is incorrect because if you were going to fill them one at a time, they have to have the same spin. Okay. Moving on, question 13. Ground state configuration for manganese. So here's where the periodic table becomes our friend. So manganese is, as we saw earlier, atomic number 25. So we find it in the periodic table right here. So for the shorthand notation, we go back to the previous noble gas. So the previous noble gas that comes before manganese is argon, number 18. Okay? So that means we're going to have the core electrons from argon. More often than not, we'll use the shorthand notation instead of writing 1s2, 2s2, 2p6, and so on. But we have argon's core electrons, and then we have to fill in the valence shell in the correct order. So after argon, we come to the 4s block of the periodic table. So we're going to fill that with 2 electrons. We go through those 2. So 4s2. And then we find manganese, which is in the 3d block. So remember, this is the n-1d that's here. So it's 3d, 1, 2, 3, 4, 5. Then we stop at manganese as the 5th element in the periodic in that block. So it's going to be 4s2, 3d, 5. And that corresponds to choice A. So choice B is wrong because we skipped 3d. Choice C is wrong because it's n-1d. So when we're in the 4th row of the periodic table, which is where manganese is, it's the 3d block, not the 4d block. And then finally, this one is wrong because we're in the 4th period, n equals 4, so it should be 4s2, not 3s2. So those are what's wrong with all of those. But if we just go through the periodic table, we can get this configuration, and that's going to be how we want to do it. Question in the back.
Do you pull the electrons from the S and
Okay, so the only exceptions where you would take the electron from the S into the D are chromium, which is 4s1 3d5. So chromium is right next to manganese, one before it. And instead of being 3d4, we take one of those s electrons and also move it up to d. And then copper, which is 4s1 3d10. So you do this when you're able to get half-filled or full-filled d subshells. Those are the only 2 exceptions that we have to worry about. As you get to the bottom of the periodic table, by the bottom I mean 4d, 5d, f elements and all that. There's way more exceptions even in there, but we're not going to worry about those. But for the part of the periodic table that we should be familiar with, these are the 2 exceptions. Any questions? All right, and now we're going on to periodic trends. So which atom or ion has the largest radius? So when we're comparing radiuses of atoms, remember that they're determined by the outermost electrons. How far are those outer electrons from the nucleus? So the first thing we want to consider is which row of the periodic table are we in, because that's probably the biggest factor that determines radius. So if we think about the choices here, we have oxygen and oxygen 2-. Oxygen is in the n equals 2, the second row of the periodic table. So the valence electrons go into the second shell. And then Cl and Cl- is n equals 3 because chlorine, Cl, is in the 3rd row of the periodic table, right here, number 17. All right, so because of this is a larger subshell. And especially since they're both nonmetals, they're both close to each other in terms of their group number, this one we would expect to be larger. So we're looking for the largest radius, so we're going to pick between Cl versus Cl-. Okay, because they're both in the n equals 3 subshell. They have a larger larger shell number. That means they're going to have electrons farther away from the nucleus. So if we're narrowing it down to these 2, so we have this relationship between neutral species and anions, which is that the anions are always larger, if it's the same element particularly. Okay, so chlorine is going to be smaller than Cl-. And the reason is when we start adding additional electrons to make anions, we have extra electrons in the outer shell, which means we have more electron-electron repulsion. And that electron-electron repulsion pushes everything apart and makes the subshell radius bigger. Okay, so when you have an anion, especially if you're comparing it to the same atom that is used to form that anion, the anion is going to be larger. So the largest one of these is going to be Cl-. So again, comparing two things at a time is helpful, and look at where they are in the periodic table. N equals 2 versus N equals 3 allows us to zero in on these two choices. All right, any questions? Yeah.
Between oxygen and oxygen, 2 negative, oxygen 2 negative would be bigger?
Yeah, so same trend applies to these ones as well. O2 minus would be bigger than oxygen, but you're never going to have a case where a second period anion is going to be larger than a third period neutral. I don't think there's any crossovers like that you have to worry about, okay?
So periods are more powerful than additional electrons.
Yeah, if you're comparing something like all the way over here to something all the way over there, you might have some crossover, but we're not going to really give you those types of ones. But if you're comparing everything that's a non-metal, everything that's in N equals 2 is going to be smaller than everything that's in N equals 3, so as far as I know anyway. Okay. Yep.
Is the general trend for like increasing radius then going down to the left?
Increasing radius is going down and to the left.
To the left?
Yes. Because when you go to the right, you're adding more protons to the nucleus, so that pulls the electrons in closer. So going left to right actually makes them smaller, even though you're adding more.
Add an electron, you're moving it to the left.
Well, as you go from left to right, you're adding an electron, but it's going into the same subshell. And because you have more protons, that subshell becomes contracted. So when you're comparing everything that's like in this part of the periodic table, all the electrons are getting added to 2p, but because there's more protons, the 2p subshell becomes contracted. Yep. Okay, moving on.
So from the left to the right.
I'm sorry.
it's getting smaller?
Yeah, left to right gets smaller for atomic radius.
Okay, so does oxygen and oxygen getting so close to each other?
Well, but usually, so like I said, going down is the bigger effect. So if you I don't think there are any N equals 3 atoms that are going to be smaller than any of these. So there's no real crossover, because as you add a whole additional subshell, you really blow out the radius. So oxygen's atomic radius is probably around 60 to 70, and chlorine's is like 100 or something. So it's a pretty big change as you go from N equals 2 to N equals 3. It's about a 30% increase or more. Okay. All right, any other questions? All right, so here we're talking about ionization energy. So for phosphorus, which ionization energy will show an exceptionally large increase over the previous one? So remember, when we're talking about successive ionization energies, that's removing one electron at a time. So the first thing we need to know is what's the electron configuration of the atom we're considering. So if we go to the periodic table, phosphorus is right here, number 15. So the previous noble gas is neon. But what we really care about for ionization energies are the valence electrons, because those are the ones that get pulled off first. So if we go to the valence shell, it's going to be 3s2, 3p1, 2, 3. Okay? So that means we have 5 valence electrons, because for p block elements, the s and p electrons, those outermost s and p electrons, are counted as valence electrons. Okay, so both of the s and p subshells count as valence electrons. So that means when we have successive ionization energies for phosphorus, each one represents removing one electron at a time. So the first ionization energy removes the first, the second, third, so on. And so on. And if we have 5 valence electrons, that means these first 5 ionization energies refer to the removal of valence electrons, and then anything beyond this, 6, 7, and so on, refers to core electrons. And there's a huge jump in ionization energy when you go from valence electrons to core electrons. So all of these are going to get bigger than each other. 2 is going to be bigger than 1, 3 is going to be bigger than 2, but the very huge jump occurs once you finish removing all the valence electrons. So after ionization energy 5, you have to start removing core electrons, and that is much more difficult to do. So which ionization energy will be an exceptionally large increase over the previous one? So the way this is worded, we should pick D, which is 6. So that means the 6th ionization energy is going to be much larger than 5, because this is the first one that involves removing core electrons. Okay, because here we're removing electrons with N equals 3. Here we have to start removing N equals 2 electrons, which are closer to the nucleus and held more tightly. Okay, questions on this one, or this concept? So also know what all these different energy terms mean. Ionization energy is removing an electron. Electron affinity is gaining an electron. So also be familiar with the definitions.
Yeah.
Oop, what?
3s2, 3p3s.
Oh, yeah. Okay, thank you for pointing that out. So it's 3p3, which means there's a total of 5 valence electrons. Sorry for that confusion. All right. Yep, sorry, go ahead. What? I can't hear you, I'm sorry. Yeah, so the valence electrons is S and P. So there's 5 of them total. That should have been a 3 all along. That was never supposed to be 5. So it's 3s2, 3p3, 2 plus 3 is 5, 5 valence electrons. Anything in the outer shell is counted as valence.
So if it goes to D, you'll add it?
So for d electrons, I don't think it's going to come into play on this exam. But if it's a p block element that has d electrons, so if it's in the the 4p or below, you still only count s and p. The d electrons won't count as valence electrons. For transition metals, they do, but we didn't really talk about that in any detail. But if anything in the p block, it's just s plus p that counts as valence. Anything in the s block, it's just the s electrons. Okay, and those are the ones that we want to be familiar with for this test. Okay. Oh, here we go, our favorite one. Calculate the lattice energy of the hypothetical ionic compound mx2 using the information below. Okay. So for this problem, it takes a while, but I think it is helpful to think of the diagram, which shows you all the steps in order. So what we're doing for these is we have an ionic compound mx2 as a solid, and we're trying to figure out the energy. So we read the problem, we want to determine the lattice energy. So lattice energy refers to the energy involved with taking the gas phase ions and bringing them together. So if we have mx2, where I guess I should have been more specific. So we're given electron affinity for x and just the first ionization energy for m. So that means, oh crap. There we go. Oh, sorry, we're given this. So anyway, we're given 2 ionization energies for m, and we're given the electron affinity for x. So that means we have m2 plus and 2x minus. Oops. Okay, so the ionization energy is the energy released when or the energy change involved with taking gas phase ions and combining them to form the compound. So this is what we're trying to find. And the way we're going to do this is in a very roundabout Rube Goldberg type fashion, which is to go around a huge circle and come back to here. And knowing that when we go around a circle, starting and ending at our ionic compound, the overall energy change as we go around is 0. We add up all of the steps, set them equal to 0, and that allows us to solve for our unknown. So there's a lot of steps we have to be familiar with. Most of them are the same, and after we do this, I'll give you an equation that works most of the time for these problems that you can remember if you don't want to worry about these diagrams. I think the diagrams are helpful for understanding what's going on, but for the purpose of this test, if you just want to remember the equation, it'll work most of the time. So the first step is always going to be breaking the compound down into its elements. So the metal is always going to exist as a solid, and then almost all cases you're going to have X2, which is going to be the form of the nonmetal. It's going to be a diatomic, 2 atoms bonded to each other. Now we can know that from the problem because the information we're giving you is, for this dissociation energy is for X2. Okay, so we tell you right here, you need the dissociation for X2 so that we can assume is the standard state for the nonmetal X.
When you wrote the M2 is that an S or a G?
That should be a G, sorry. So the the lattice energy refers to gas phase ions going into a solid. So we have to take everything into the gas phase before calculating lattice energy, before determining that. So the way we do this is we first break down the compound into its elements. This is called the delta E of formation. So formation is, but it's the negative of that. So formation is forming the compound from the elements. If we're doing the reverse process, we take the negative. So going back to our given information up here, delta E of formation is minus 443. So that means this first step is a plus 443 energy change. So for this first step here, we never have to modify the number. We just have to change the sign if we're writing out this cycle, because we're doing the reverse process. So that first step is always the same for all these problems. And then the second step is usually is always the same as well. So we're going to take our metal as a solid and change it to the gas phase, because all of these energies for ionization and finally for the lattice energy are in terms of gas phase species. So we have to take our solid and change it to a gas, and that energy is involved as well. So the energy that's involved with that is called the sublimation energy, or sometimes the atomization energy. And that's given to you here. We didn't actually, so I gave it to you as delta H, but it's the process of going from a solid to a gas is 124 kilojoules per mole. It might be abbreviated as sublimation energy, but it's that process here. Metal solid to metal gas, 124 kilojoules. The next step is going to be ionization of the metal. Okay, so now that our metal is in the gas phase, we can apply the ionization energy, because ionization energy refers specifically to gas phase species. So in this case, we're going up to metal 2+. We're losing 2 electrons. Right now we're not touching the nonmetal part, just the metal. So M2+ to 2 electrons. We go up here, and we're given the sum of these first 2 ionization energies for the metal. So remember, if we're removing 2 electrons, that corresponds to 2 ionization energies, so we need the sum of those 2, which is directly given to us as 743. If we had them individually, we'd have to add them together. But it's 743, so this is the first plus second ionization energy. Still recording. I want to make sure my free video software doesn't have like a time limit or something. So 743 is the energy required to remove 2 electrons from the metal, and that's given to us also. And then finally, the last step we have to do that involves input of energy is breaking the bond. So here we have X2. We're done with the metal, right? We've made gas phase M2+ cations, which is going to be what's going to be involved in this last step here. But we still have to break our nonmetal apart first into atoms, and then we have to form ions from that. So the first step is to break this apart into atoms, 2 X's. Okay, because it's X2, that means there's 2 atoms of X. And so when we dissociate it, we get M2+, still as a gas, 2 electrons, and then 2 gas phase X atoms. That's the top point of our diagram. This is what we call the BDE, the bond dissociation energy. And because we have 1 molecule of X2 involved, we just use that number as given to us. So for X2, the bond dissociation energy is 256 kilojoules per mole. So that's the number we use, 256. Okay, so it takes 256 kilojoules of energy to break apart that bond. We talked about bond dissociation in the context of covalent bonds, and that's what that number refers to. And then finally, the last step, we have 2 electrons, 2 gas phase atoms, and we're going to combine those to make our 2 X- anions. So we just draw an arrow down to this step here, which is just taking, again, the electrons and adding them to X, and that's referred to as electron affinity. Electron affinity is the process of adding electrons to a nonmetal, or to any atom, really. But in this case, it only applies for the nonmetal. Okay, so if we do this, though, we have 2 X's that are each taking on 1 electron. So we have to double that energy because it's happening twice. So we have to do 2 times the electron affinity for X, because there's 2 atoms of X that are each gaining 1 electron, so it has to happen twice. So if we go back up to our given information, the electron affinity for X is minus 325. The first electron affinity is almost always negative. So that means when we add 2 electrons to 2 atoms of X, we release 650 kilojoules of energy. We have an energy change that is minus 650. All right, it has to happen twice. All right, so now we have this cycle, and our only unknown is the lattice energy, which we have to solve for. As we go all the way around, the sum of all of these should equal 0 once we add in our lattice energy. So then the work becomes, all right, we have, here we go. So 443, so we're set it equal to 0. 443 plus 124 plus 743 plus 256 minus 650 plus the lattice energy, which is our unknown, and we just solve for that. And we should get minus 916 kilojoules. And again, because this is in the format of a Blackboard test, We specify 1 decimal place in kilojoules. Oh, I guess I didn't specify kilojoules, but it should be in kilojoules, and it's going to be minus 916.0. Now, if you forget the 0.0, you're not going to be counted wrong, but we do that for your safety to make sure you don't round it off too much. So if we specify 1 decimal place, enter it in even if it's a 0, but in this case it wouldn't matter because it's an exact number. But just you're following the instructions. So that's how we do it. Now, as I mentioned at the beginning of this, there is an equation you can use that works most of the time. I'll tell you when it doesn't work, okay? But just about all the time. So the lattice energy is equal to the energy. So if we have a compound that has this formula, MM, so the subscript is on the metal is M, and the subscript on the non-metal is N. The lattice energy is going to be equal to the energy of formation minus M times the sublimation energy, which is the energy required to take the metal into the gas phase, minus M times the ionization energy for the metal. And again, if it's 2 ionization energies, you have to add both of those together, but it's however much energy is required to ionize the metal, minus N over 2 times the bond association energy, which is the bond association energy for X2. So this works if X2 is the form of your nonmetal, which is the case almost all the time. And then finally, minus N times the electron affinity for X, which is the energy involved with gaining an electron to X. So this equation will work if it's this type of compound, which is generic ionic compound where X2 is a gas. Now here's the exception. So if you might see one on the test where it's a sulfide, and sulfur exists as S8. So this is going to be N over 8 if X is equal to sulfur. Okay, so that's one exception. That N over 2 becomes an N over 8 if it's sulfur, because the reason this is N over 2 is because you have, if you have N X's in your formula, that's going to give you N over 2 X2s, and you're going to multiply that by the bond association energy. But if it's going to S8, when you break it down into its elements, you have to take N over 8 because it's S8. So that's one exception. And then if this is given to you in the problem, delta E, we'll keep it consistent. You'll have to include this term minus delta E vaporization. And the reason for that is because Br2 is a liquid. So all of these processes refer to gas phase ions. And in one case, if it's a metal bromide, when you break it down into the elements, you get Br2 as a liquid, and you have to first take that into the gas phase as part of your cycle. And that includes a vaporization energy, which we may give you as a separate term. It could just be sometimes included in the dissociation. So if you're given Br2 liquid to 2Br gas, so if you're given the value for going from the liquid to the gas phase atoms, just use that directly. But sometimes you'll have a separate step where you have the energy involved with taking the liquid to the gas, and then the energy involved with taking the gas phase Br2 to 2Br. So that's one exception, but don't worry about that too much because I don't know, it's not likely to come up for you. But these ones, this equation here will be useful for just about all of them, except for if you have a sulfur, you have to modify that term. So I still think it's helpful to understand this cycle because it tells you all the steps. Make sure you don't forget one. It shows you where everything is going as you do all these different terms. But if you want to just remember the equation as a helpful guide, that could be useful as well. Okay? So my recommendation is just to practice these over and over again until they become close to second nature. I don't know if they ever will, but. By 1/2 or by? Why do I have to multiply what by 1/2?
Multiply by 2.
Multiply by 2. Which one?
Very last
The electron affinity.
Okay, in the actual problem. Okay, sorry, I couldn't hear you very well. The reason I multiply this by 2 is because there's 2 x's each taking on 1 electron. So the electron affinity refers to x going to x minus. Here we have 2x going to 2x minus, because we have, our formula has mx2, so there's going to be 2x minus anions. So each of those is going to release 325 kilojoules when it gains an electron. It's happening twice, so we have to double that. So that comes from the stoichiometry. And so in this equation here, n times the electron affinity. There's 2 x's in the formula, so we have to double electron affinity to account for that. Okay? Okay, so that's the long one, so definitely on the test, save some time for that. Like I said, it's among the most difficult problems we'll do this semester, so let's get it out of the way. Yep?
398 at the very bottom, so
Yes, so occasionally we'll pull a fast one on you and give you information that you don't need. So here I gave you the ionization energy for X, but remember ionization energy is removing an electron, and when we're forming an ionic compound, we don't remove electrons from the nonmetal, we add them to the nonmetal. So we don't need ionization energies for X, and we don't need electron affinities for the metal, because those refer to the opposite process from what's actually happening. So occasionally you'll have information that you don't need, so that's again where it's helpful to understand all the steps that are involved and be able to piece it together one by one. Okay? We're almost there. So finally, pick the strongest bond from each of the following pairs of compounds. All right, so here we're talking about covalent bonds. So we have to be able to draw Lewis structures for some of these to be able to figure out what the bond looks like. So in choice 1, we're talking about the bond in O2 or the oxygen-oxygen bond in H2O2. So for O2, we have, we'll do this quickly, 12 electrons. Each of them has each of them has 6 valence electrons. So when we draw the Lewis structure, we have oxygen, oxygen. Oxygen likes to form 2 bonds, and so we get a double bond. Okay, so that's the Lewis structure for O2. I'm skipping some steps now in the interest of time, but that's what it would look like. And then for H2O2, we have, in this case, 14 electrons. So we're going to have this structure, O, O, H, H. Because oxygen likes to form 2 bonds, and because of the number of electrons we have, we complete the octets. So this has 2, 4, 6, 8, 10, 12, 14 electrons. So we could take, if we go through all the steps to draw this, I recommend you get familiar with some of the patterns, which is things like oxygen tends to form 2 bonds, especially in neutral compounds. Nitrogen forms 3 bonds, carbon forms 4. All those things you'll see if you do enough of these. But those are the structures. So in this case, we're comparing a double bond to a single bond. So double bonds are stronger than single bonds, and so that's going to be the one that's higher. So if you're comparing 2 bonds with different bond orders, the one with the higher bond order, the one with the more bonds, is going to be stronger. So that's the stronger of the 2 here. In choice 2, we have H2S versus H2O. So both of these are single bonds. Now we don't even have to draw the structure because the only type of bonds that hydrogen forms are single bonds. So we're never going to have double bonds in this case. So it's HS versus HO. And when you're comparing 2 bonds like this, we want to look for which one is the shorter bond, and that's going to be the stronger bond. And that comes from the atomic radius. So oxygen is right above sulfur on the periodic table. So oxygen is smaller than sulfur because it has a 2p valence shell versus a 3p. So oxygen is smaller, which means the OH bond is shorter. And that means it's going to be stronger. Okay, so the closer together the nuclei are, the stronger the bond is. And because oxygen is smaller than sulfur, this bond is going to be shorter, and that's going to make it stronger. And then finally, the last one, the carbon-oxygen bond in CO2 versus CH3OH. Okay, so CO2, if we draw the Lewis structure, 2 bonds to, we put the least electronegative atom in the center, which is carbon, and then 2 bonds to oxygen gives us double bonds. Carbon likes to form 4 bonds, so that all works here. Again, we could do the whole electron counting and drawing the single bonds and then completing the octets. That works too, but I'm going to skip that for now since we've been here for a long time already. And then finally, if we do CH3OH, we form single bonds to the hydrogens. When you have a formula like this, the hydrogens are going to be bonded to the atom that they're closest to. So if it says CH3, that means those 3 hydrogens are bonded to the carbon that is closest to, that comes before it. And then the OH, this H is going to be bonded to the oxygen that comes before it. So when you see a notation like this, the hydrogens get bonded to the atom that comes before it. So CH3OH means we have 3, and those, of course, are single bonds because that's all hydrogen makes. And then the carbon is going to be bonded to the oxygen, and the oxygen is going to be bonded to the hydrogen. If we fill in lone pairs, we get this. So again, recognizing patterns. 4 bonds to carbon, 2 bonds to oxygen, a total of 3 plus 4 is 7, plus 1 is 8, plus 6, we have 14 valence electrons, 2, 4, 6, 8, 10, 12, 14, so everything checks out. So that's the structure, and again, single bond to double bond. We have a carbon-oxygen double bond versus a single bond, and the double bonds are always going to be stronger without any other information given, okay? So it's O2, H2O, CO2, that's choice B. All right, so that's how we make those comparisons. Think about the bond order and then also the bond length if it's the same bond order, whether it's shorter or longer. Yeah? So that comes down to the atomic radius. So the length of a bond is essentially the sum of the atomic radius of the two atoms that are bonded to each other. So they both have hydrogen, so the atom that's different is oxygen versus sulfur. If we go back to the periodic table, oxygen is above sulfur on the periodic table, which means that oxygen is smaller than sulfur. So because oxygen is smaller, the bond is expected to be shorter. Okay? Yep?
So regardless of the number of single bonds in the other one, if one has just even one double bond.
Well, we're comparing specific bonds. So here it's the carbon-oxygen bond in CO2 versus the carbon-oxygen bond in CH3OH. So if we look at that, both of those are double bonds, and this is a single bond. So some would have both carbon-oxygen single and double bonds. We have to specify which one we're talking about. But in this case, it's only single bonds or only double bonds for all these examples. Yep. Yes, in a way. It has, so the atomic radius is a different trend because it increases as you go down and to the left. So it's actually the opposite trend of electronegativity, but it does have a periodic trend that's very predictable. And if it's if something is above something else on the periodic table, that means it's smaller. Okay. All right. And now we have a question about the least polar bond among the following. Okay. So here again, it's useful to compare 2 at a time. So if we compare the first, we don't have CS anymore, do we? CCl, sorry. Okay, so if we have carbon-oxygen versus carbon-chlorine, remember that the more electronegative atom is going to have the partial negative charge, and the other one's going to have a partial positive charge, and the polarity, the size of the polarity depends on the difference in electronegativity between the 2 atoms. So if we go to the periodic table, we have carbon versus oxygen. So carbon is up here, oxygen is to the right. So electronegativity increases as we go to the right. So this one is definitely going to be delta minus, delta plus. And then carbon versus chlorine, it's a little bit more difficult of a comparison because it's down and to the right. But because it's 1 down and 3 to the right, we would assume that chlorine is more electronegative than carbon. Really, the only thing that's less electronegative than carbon are the things directly below it. Everything else that's to the right of it is more electronegative. That's a good thing to remember. So because of this, chlorine is still more electronegative than oxygen, but chlorine is less electronegative than oxygen. Okay, because oxygen is the second most electronegative atom on the periodic table. So because of this bond is going to be less polar. So that means carbon-oxygen is greater than carbon-chlorine because we're looking at delta En, the difference in electronegativity. So the difference in electronegativity is smaller here than it is here. This is probably not the best one to pick because there's a little bit of ambiguity here, but oxygen is both of these are more electronegative than carbon. Oxygen is more electronegative than chlorine, so this is going to give you a more polar bond, a larger difference. All right, the rest of them are a little bit more straightforward. So if we have, we're picking the least polar bond. So out of these 2 is carbon-chlorine, so that's the winner so far. So if we take that carbon-chlorine bond and compare it to the next one, carbon-fluorine, if we go to the periodic table, Fluorine is more electronegative than chlorine. It's above there. Okay, so remember, as we go up, we increase electronegativity. Fluorine is the most electronegative atom on the periodic table, so that's, with carbon, the most polar bond you can make among all the nonmetals. So this is definitely more polar. So CCl is still our least polar one. And then finally, if we compare that one, so far carbon-chlorine is winning. But if we compare carbon-chlorine to silicon-chlorine, here they have a common atom, chlorine, which is electronegative than both carbon and silicon. So if we move down the periodic table, silicon is less electronegative than carbon, which means it's going to have a larger difference in electronegativity compared to the carbon-chlorine. So this one's more polar, which means carbon-chlorine still is our winner. Okay? So compare them two at a time, and it's the difference in electronegativity. This probably wasn't the best choices of examples because there's a little bit of ambiguity whether carbon or chlorine is more electronegative. But you look for the difference in electronegativity, which is how far apart they are, lower left to upper right in the periodic table. And that tells you which bond is more polar. All right, this one we did in class today, so I guess I won't spend a lot of time on it. I didn't realize I duplicated these. That was a stupid mistake. But which of the following is the most important resonance structure for chlorate? And as we talked about in class today, it comes down to evaluating formal charges, number of electrons, and octet rules. So in this case, this answer choice is a little bit different. So all of these have the correct number of electrons this time. None of them are missing electrons. So now we have no choice but to evaluate octet rules and as well as formal charges. All of them also obey the octet rule. The oxygen has 8 electrons in each case, because it's either 2 double bonds and 2 lone pairs, or a single bond with 3 lone pairs. So we have octets around all of the oxygens. Chlorine has at least 8 electrons around it, 8 or more, so that's okay. Chlorine's in the third row of the periodic table, so we can expand its octet. So now we just need to evaluate formal charges. So for this one, we have zeros in all the oxygens, because oxygen has 6 valence electrons, 2 bonds, and 4 lone pairs is 0. And then chlorine has 7 valence electrons. It has 6 bonds, and a lone pair is -1. So here are -1 formal charges on chlorine. For this one, we have a -1 on oxygen, and zeros all the rest of the way around. When we have oxygen single bonds, it's going to be -1. 0 on that oxygen, and in this case the chlorine is going to be +1. 7 minus 4 bonds minus 2 lone pair electrons is +1. So we have this distribution of formal charges. And then finally on the last one, we have -1s on all of the oxygens, and then chlorine is going to be 7 minus 3 minus 2 is +2. Now, as I said in class, I can't think of a stable or good structure that has a +2 formal charge, so this one we can eliminate right away. And from there, we want to minimize the number of formal charges. So all the rest are +1s and -1s, but choice C has 3 formal charges compared to only 1 for the other ones. So we think it's going to be one of these two. And as we talked about in class today, we would prefer to have the negative formal charge on the more electronegative atom, which is oxygen. So that's why choice B. So that's just a review of what we did in class, but I guess for the people that skipped class, they can now see that on the video. All right, so that's that one. Sorry for the duplicate. And then finally, the last type of problem we're going to do today is using bond strengths to estimate the energy change for a chemical reaction. So here we're taking covalent compounds and rearranging all the bonds to make new compounds. And we want to figure out how much energy is involved in that process. So the bond strengths on the left side, the reactant side, are not likely to be exactly the same as the bond strengths on the product side. And because of that, energy could either be absorbed or released as those new bonds are formed. So the way we do this is we sum up all of the bonds from the product side, the reactant side and the product side, and then we subtract them. So to be able to do this, we need to be able to draw good Lewis structures for all of these compounds. Okay, so that's the first step. So for COCl2, if we do this, we have this Lewis structure. And again, a lot of the patterns that we've been seeing are going to hold true here. 4 bonds to carbon, 2 bonds to oxygen, 1 bond to outer halogen atoms. So if the halides are on the outside, fluorine, chlorine, bromine, and so on, those tend to have a single bond. And a double bond for oxygen, and so on. So we can do that in longhand if we wanted to. If you need me to go over that, I gladly will do that later. But that's the Lewis structure, which means we have a carbon-oxygen double bond in that molecule. So that means, and then H2O we should be very familiar with. It's just this. Okay, hydrogen only makes single bonds. So on the reactant side, we have CO, Cl2, and H2O. So that we have one CO double bond. Okay, that's this bond here. That's going to be 745 kilojoules. So we go to our list of bond strengths. You wouldn't have to memorize these, but we're given C double bond O is 745. So we need to know the bond order to be able to do this properly, whether it's a single, double, or triple bond. So for C double bond O, it's 745. We have 2 carbon-chlorine bonds, okay, because we have COCl2, so one chlorine bond, one bond to chlorine, a second bond to chlorine, 2 of those. So you have to double that number, which is 339 from the table. And then finally, in water, we have 2 OH bonds. Remember, we have to count each bond individually. So there's one bond to this first hydrogen, another bond to the second hydrogen, H2O. So we have 2 bonds. Remember, the total number of bonds will be, is n minus 1. So if you have 3 atoms, like we have H2O, we have to have 2 bonds holding those 3 together. Okay? So when we do that with 2 OH bonds, it's going to be 2 times 467, which is 934. And then we go to the other side of the arrow, which is the product side. All right, we need Lewis structures for this. We did CO2 earlier. It's carbon-oxygen double bonds. Whoops, I'll draw that down here. So that's CO2, so it has 2 carbon-oxygen double bonds. So we have to do 2 times the CO double bond strength, which is 745. And then we have HCl. That has to be a single bond because hydrogen only makes single bonds. However, we have 2 of those because that's what this number in the chemical reaction tells us. We're forming 2 molecules of HCl, so we have 2 HCl bonds, 2 hydrogen chlorine bonds. So 2 times 427. So for each of these reactant and product sets, we're going to sum them up. So we add these 3 numbers here, 745, 678, 934, and we get 2357 kilojoules, assuming I did my math right. We add the sum of the bonds on the product side, which is, again, 2 CO bonds, 2 CO double bonds, and 2 HCl bonds. And we get 2341. Or sorry, 44. Can't read my own writing sometimes. Okay, so we have these 2 numbers, and then remember that delta E is going to be reactants minus products because we put energy in to break all of these bonds, and then we release energy when we form all of the bonds on the right side of the arrow. So it's going to be reactants minus products. So it's going to be 2357 minus 2344. So it's a very small number, but slightly positive, plus 13 kilojoules. All right, so in this case, what this tells us, this positive number, is that the bonds on the reactant side are stronger than the bonds in the product. All right, that wraps it up. I'll gladly stick around and answer any individual questions you have, and I'll migrate back to the office after this if you want to stop by there.